All right, so this is a review for multivariable calculus or calculus 3 course. We're doing an exam review for a couple chapters that involve vectors and lines and planes and just sort of general introduction to three-dimensional space. I'm just going to go through some problems here. First problem, we have vector A is 3, negative 1, 4. Vector B is 1, negative 1, 0. And then we're supposed to just do some routine calculations. So the first one is 2A minus 3B. Here. So 2A is 2 times the vector 3, negative 1, 4. Minus 3, B is the vector 1, negative 1, 0. Now when we multiply a vector by a scalar, we just sort of distribute this 2 to each of the 3, negative 1, 4. And this 3 to each of the 1, negative 1, 0. So what we get, here's 2 times 3 is 6. 2 times negative 1 is negative 2. 2 times 4 is 8. Minus 3 times 1 is 3. 3 times negative 1 is negative 3. 3 times 0 is 0. And then the subtraction with vectors is just component-wise. So we get 6 minus 3, that's 3. Negative 2 minus negative 3, it's negative 2 plus 3, that's 1. And we get 8 minus 0, that's 8. So our answer here is the vector 3, 1, 8. Next question, we've got A dot B. So that is 3, negative 1, 4, dotted with 1, negative 1, 0. And now we just want to do a dot product here. So what the dot product does is we take the first component of A times the first component of B, 3 times 1, second component times second component, and we're going to add that. So plus negative 1 times negative 1, plus 4 times 0, third components. Here, and what we get with our dot product is going to be a scalar. 3 plus 1 plus 0, that works out to be 4. Next question, we're going to do a cross product. Cross product of two vectors should give us another vector back. Got our A and B written down up here. So we're looking for 3, negative 1, 4, crossed with 1, negative 1, 0. So there's a few different ways to sort of do the bookkeeping for this calculation. I like to do this as a determinant of matrices, or of a matrix. We have I, J, K, go up here, and I put the first vector, 3, negative 1, 4 in the second row, and the second vector, 1, negative 1, 0, third row, and then I'm going to do a cofactor expansion along the first row, and get I times the determinant of negative 1, 4, negative 1, 0, so that's negative 1 times 0. I'm going to cross out the column and the row. I'll just write that out. Negative 1, negative 1, 4, 0. And then it's a minus j times cross out the column and row of j. Get a 3, 1, 4, 0, 2 by 2 determinant, and plus k. Note we get a plus I and a minus j and a plus k. And we get a 3, negative 1, 1, negative 1. And these just work out to be, see, negative 1 times 0 is 0, minus 4 times negative 1 is plus 4. So we get 4i. So we have 3 times 0 is 0. 4 minus 4 times 1 is 4. We're going to subtract 4. This determinant is negative 4. The negative out there makes this a plus 4j. The k is 3 times negative 1 is negative 3. Then we're going to subtract a negative 1. That's going to give us a minus 2k. So you could leave your answer like this. That's fine. In vector notation, maybe the other notation we're using, I would write this as 4, 4, negative 2. Note, if you want to check this, you can take a dot product of this vector with both of these, and individually 4, 4, negative 2, dotted with 1, negative 1, 0, should give you 0. That is, they should be perpendicular or orthogonal. 4, 4, negative 2, dotted with 3, negative 1, 4 should also give you 0. So if you do 4 times 1, that's 4. Negative 1 times 4 is negative 4. Well, I'd get a 0 for sure. 4 times 3 is 12. Negative 1 times 4 is negative 4. Those add to 8. Negative 2 times 4 would give us a negative 8. That would give us a 0 as well. So the answer checks out. Okay, now the magnitude of A. So A was the vector 3, 1, 4. We do the magnitude of a vector. Sorry, 3, negative 1, 4. What we do is we take the square root of, we take the first component squared plus the second component squared plus the third component squared. If you think about it, this is really the square root of A dotted with A. And in our case, that is, let's see, square root of 9 plus 1 plus 16. 9 plus 1 is 10, plus 16 is 26. So we get a square root of 26 as our answer. Next up, we want to find a unit vector in the direction of b. Just write down b was 1, negative 1, 0. So b happens to be 1, negative 1, 0. And we want to find a unit vector that points in the same direction. So what we're going to do, the standard sort of operation to get our unit vector, call that u, is you do b divided by the magnitude of b. So it's the vector 1, negative 1, 0, divided by the magnitude of 1, negative 1, 0. So that's 1, negative 1, 0, divided by the square root of 1 squared plus negative 1 squared plus 0 squared. So that's 1, negative 1, 0, divided by, this is going to work out to be 1 plus 1 is 2, plus 0, square root of 2. And you can take a vector, divide by a scalar, and sort of do that component-wise. And so we get 1 over the square root of 2, negative 1 over the square root of 2, 0. You could rationalize denominators, multiply by square root of 2 over square root of 2 if you want to. I think this answer is fine. If you wanted to rationalize that, you'd get square root 2 over 2, negative square root 2 over 2, and 0. Okay. Angle between A and B. So you have two vectors. You want to find the angle between them. What we're going to use is the formula A dot, A dot B is the magnitude of A times the magnitude of B times cosine of theta, where theta is the sort of angle between the two vectors. So rearranging this, we get theta should be an inverse cosine of A dot B over magnitude A times magnitude B. We get an inverse cosine, arc cosine, A dot B. I believe we found that already up here. You could run the calculation again. But A dot B was 4. A dot B is 4. Magnitude of A was one of the particular questions here. I believe that's the square root of 26. Magnitude of B, let's see. Well, we used that to find the unit vector. The magnitude of B was the denominator here. That was the square root of 2. You could also just run through these calculations on your own. Note, if I simplify this, I get cosine inverse of 4 over 2 square roots of 13. I could factor out a 2 from the 26 and do 2 times 2 is 4, square root is 2, which works out to be cosine inverse of 2 over square root of 13. So that's a fine answer. You could convert that into degrees or radians with an approximation using a calculator if you'd like to. Okay. Now we want to find the area of the parallelogram determined by A and B. So we've got a parallelogram, A, B. We want to find the area. That area, one way to calculate that is you take A cross B and you find the magnitude of A cross B. So we could go back through our calculation for A cross B. We could just redo that. In this case, I'm just going to copy that over. So A cross B, so this one here, it's 4, 4, negative 2. So again, if you hadn't done that question already, you could just redo this. It's 4, 4, negative 2. I just need to find the magnitude. It's the square root of 4 squared plus 4 squared plus negative 2 squared. It's the square root of 16 plus 16 plus 4. 16 plus 16 is 32, plus 4 is 36. Square root of 36. We get an area of that parallelogram of 6. Next one. Find a vector projection, find the vector projection of A onto B. So if we recall, again, A was 3, negative 1, 4. B, our vector, I believe it was 1, negative 1, 0. I want to just check that. Yep, we've got a 1, negative 1, 0. Whoops. Not where it was. -1, -1, 0 for B. And we do this projection here of A onto B. The picture, when you look at this, is you've got a vector here. Let's see, this vector is A. And then there's some other vector B here. And what we're looking for is really this vector here, where we get a right angle. So that red vector is the projection of A onto B. So that's really what we're looking for here. And the formula for that, so we're going to do a projection of onto 1, -1, 0. We're going to project 3, -1, 4. That formula is I'm going to dot my two vectors, 3, -1, 4, dotted with 1, -1, 0. And I'm going to divide by the magnitude of the vector I'm projecting onto. That's B, or 1, -1, 0 in this case, but that magnitude squared. And then I'm going to multiply by the vector 1, -1, 0. So this is going to give me a vector. This really gives me some sort of multiple of this vector here. So we're going to get, oh, sorry, I actually messed up my projection here. I have to go back looking at this. This is not the projection of A onto B. Whoops. Well, let's draw A in here again. So A goes here. What we want to do, we do want to drop this perpendicular, but a projection of A onto B should be in the direction of B. So I messed that up there a bit earlier. So we get this projection here. And you'll notice here what I was thinking of is that what I'm getting is a multiple of B, 1, -1, 0, so that vector should point in the same direction as B, or perhaps in the opposite direction. This sort of perpendicular vector should dot to 0 with B, but that's not going to happen here. Okay, now we need to do the calculation. We get 3 plus 1 plus 0, that's 4 when we do the dot product. This bottom is going to be 1 squared plus -1 squared plus 0 squared. We're going to multiply that by 1, -1, 0. So we're going to get 4 over 2 on the bottom times 1, -1, 0. That's 2 times 1, -1, 0. So that gives us the vector in the end, 2, -2, 0. So that's really this red vector here. Okay. Now that was projection, vector projection. Let's find the scalar projection of A onto B. So the scalar projection, all this is when it's scalar projection, is it's really the magnitude of the projection of A onto B. So you could, given that we have the vector projection, just take the magnitude of that vector. That would be fine. Another calculation here is you could say this is A dot B divided by the magnitude of B. Note, not squared like we did up here, but we just have one B there. Essentially, we're using the other B to change this, oops, sorry, the other magnitude of 1, -1, 0. Take this minus one of those to get a unit vector here. And we need an absolute value of A dot B as well, because A dot B could be negative. So in our case, what we get is A dot B is 4. Magnitude of B is square root 2. So we get 4 over square root of 2. It's probably an okay answer. It might be a good idea to multiply top and bottom by square root 2 to rationalize that denominator. So we get 4 square root 2 over 2, which is 2 square roots of 2. So the scalar projection of A onto B is 2 square root of 2. Note that's going to be the same thing as the magnitude of this 2, -2, 0, of the vector projection. Okay, so end of that A and B vector calculations. New question. We want to find the equation of the line containing the points 3, -1, 4, and 2, -1, 0. So when we say the equation, this is going to be a parametric equation. And so the general setup here is we're going to just do an R of t. What we're going to get is pick one of the points. It doesn't actually matter which one. I'm going to pick the first one. So you can take the point plus multiples of the vector between the 2 points. And the way you get that vector is you're going to subtract component-wise. So let's do 2 minus 3, that's -1, -1 minus -1 is 0. 0 minus 4 is -4. You could have subtracted in the other way. You could have used the other point here. When you put this all together, what you get, let's see, this is 3, -1, 4. When you distribute the t, you get -t, 0, -4t. You add component-wise, you get 3 minus t, -1, 4 minus 4t. So this is really your parametric equation for the line that contains these 2 points. Note the way we did this. If you plug in t equals 0, you'll get 3, -1, 4, the first point. And if you plug in t equals 1, 3 minus 1 is 2, -1, 4 minus 4 times 1 is 4 minus 4 is the 0. So this is the point when t equals 0. This is the point when t equals 1. Sometimes that's nice to know. Okay, next sort of standard calculation here is we have 3 points, and generally those points will determine a plane. We're going to find that plane. So the first thing we're going to do is let's just write down the points here in a drawing. So we have 3, 2, 1. We have -4, 0, 4. And then we have 0, -1, -2. I'm going to try and find a normal vector to the plane. To do that, I need 2 vectors in the plane. And so I'm going to do at least, well, 2 subtractions here of points. So this vector here, let me write that in red, it's going to be -4 minus 3. That's -7. 0 minus 2, that's -2. 4 minus 1, 3. So the vector from 3, 2, 1 to -4, 0, 4 is -7, -2, 3. That's one vector that's sort of in the plane we want. The other vector from 3, 2, 1 to 0, -1, 2, so 0 minus 3 is -3, -1 minus 2 is -3, -2 minus 1 also -3. So here's another vector that's in this plane. Now, what we need for the equation of plane is we need a normal vector and a point on the plane. We've got 3 points on the plane, so you can pick any one of those. So you only get that normal vector. That normal vector is going to be the cross product of any 2 vectors in the plane. So I'm going to take -7, -2, 3, and cross that with -3, -3, -3. So you get, here, let's see, -7, -2, 3, -3, -3, -3. Let's see, in the I component, we get -2 times 3 is positive 6, minus 3 times -3, that's minus -9, so plus 9, that's a 15. For the J component, -7 times -3 is positive 21. 3 times -3 is -9, so we're going to add 9. That's 30, but because it's the J, it's a -30. And then the K would be -7 times -3 is positive 21. Minus 2 times 3 is 6. 21 minus 6, that's a 15. So this is our normal vector, 15, -30, 15. You could now write an equation. You could do 15, a few ways to do this. 15 times, let's pick the point 3, 2, 1 here, sort of arbitrarily pick a point. 15 times x minus 3 minus 30 times y minus the 2 plus the 15 times z minus 1, and then that should equal 0. So essentially we're saying the vector 15, -30, 15, and the vector x minus 3, y minus 2, z minus 1, if you take the dot product of those 2 vectors, you should get 0. So the 15, -30, 15 is a normal vector. X minus 3, y minus 2, z minus 1 is some random vector in the plane, or arbitrary vector. Now, you could do a couple things with this. You could distribute this out here. Something else you could do is, if you notice this vector, maybe this normal vector, let's do this in a little different way, is you have a factor of 15. So this is 15 times the vector 1, -2, 1. So if 15, -30, 15 is normal to plane, so is 1, -2, 1. So one thing I might have done is just use this smaller vector here to work with. Just makes the calculation easier. There's certain places you could have noticed part of this 15. For instance, you could have rewritten -3, -3 as 3, or even -3 times 1, 1, 1. But still, we got sort of a factor of 5. So if you have the 1, -2, 1, you could rewrite this as just x minus 3 minus 2 times y minus 2 plus 1, which I don't need to write, times z minus 1. It's just a little bit simpler. Another thing you can do with either of these, let's just do the 1, negative 2, 1, is you could solve this here. Let's just do that first. So you get x minus 3 minus 2y plus 4 plus z minus 1 equals 0. That gives you x minus 2y plus z equals, let's see, we have negative 3, negative 1, that's 4, plus 4. That's actually a 0 there. So your point is x minus 2y plus z equals 0. Now, something you could have done once you had your normal vector 1, negative 2, 1 is written this down as x, when it's going to be x minus 2y plus z. It's going to equal some constant. And just to evaluate that, whoops. So evaluate that expression at any of the points here. So let's do 3, 2, negative 1. So 3 minus 4 is negative 1, plus 1, that tells me 0 there. So I don't need to, let's make that a little nicer. I don't need to actually expand this out as x minus 3, y minus 2, z minus 1. I can just plug in 3, 2, 1. 3 for x, 2 for y, 1 for z, and see what I get. Now, the idea is, and a nice check on this, is you should be able to plug in the other 2 points as well. So negative 4 times x plus 0 y, so negative 4 for x, 0 for the y, 4 for the z, negative 4 plus 4 is 0. If you use the point 0, negative 1, 2, you get a positive 2 from the y, minus 2 from the z. That'll give you 0 as well. So you can see this equation is in the form of a plane, and and these 3 points are all on that plane, so that you can know right away is the answer. Okay, next question here. Let's find the equation of the plane containing the line r of t is 2 minus t, 3 plus t, comma 5 plus 2t, and the point 5, 3, 0. So we're finding the equation of a plane. We need a point on the plane, which we have. That's the 5, 3, 0. We also need a vector that's normal to the plane. Now, because this vector is, or this line is in the plane, you can pull off sort of the direction vector of the line. That'll give you a vector that's in the plane, not a vector normal to the plane. So we're going to have to create something else. So our geometry here, let's draw this out. We have our line, and then you have your point 5, 3, 0. Now, this particular vector, or parameterization, if I sort of pull apart the components without the t and then the parts with the t, I get 2, 3, 5, so there's no t's, plus t times negative 1, 1, 2. And if you think about how you construct the parameterization of a line, that means that we have a point on the line, 2, 3, 5. And that means we have a vector in the direction of the line, negative 1, 1, 2. So this vector here is negative 1, 1, 2. Now I don't actually know if that vector goes this way or perhaps in the opposite direction, but it's not going to really matter here. So all of this is in the plane we're concerned about. And so we have to get a normal vector to the plane. We only have one vector, so we have to create a second vector. So that other vector, we can take our 2 points and subtract them. So I'm going to do 5, 3, 0 minus 2, 3, 5. When you do that, 5 minus 2 is 3. 3 minus 3 is 0. 0 minus 5 is negative 5. So now we have a new vector, and then the negative 1, 1, 2 are both in the plane. So we can get a normal vector. Our normal vector should be the cross product of those two vectors. So we're going to do I, j, k, 3, 0, negative 5, and then negative 1, 1, 2. So that will give us a normal vector to the plane. So we'll get our I component, we get a 0 minus negative 5, that's a positive 5. J is going to be 6 minus 5, that's a 1, because j it's a negative 1. K is going to be 3 minus 0, that's a 3. So our normal vector is 5, negative 1, 3, and we have a point 5, 3, 0. So the method that I like to do is just write down 5x minus y plus 3z. I know that should be constant for every point in the plane, in particular for 5, 3, 0. So if we do a 5 times 5, we get 25. minus 3, that's 22, plus 0. So that should get a 22, because if I plug in 5 for x, 3 for y, 0 for z, I get a 22. So that just has to be the right equation. Okay. Another equation of the plane question. So I find the equation of the plane parallel to the plane 3x minus 4y plus z equals 7 and containing the point 3, negative 1, 2. So if I have two planes that are parallel, that's going to mean they have the same normal vector. So our normal vector is the same as the normal vector of this equation. But we can actually just read that off as a 3, negative 4, 1. So parallel planes, we get the same normal vector. So in our case, we're going to end up with an equation like 3x minus 4y plus z. That's the same left-hand side. What's potentially going to change is this right-hand side will be something other than 7. How do we find out what that is? Well, we need to have the point 3, negative 1, 2 on the plane. So you could just plug in 3 times positive 3. 3 times 3 minus 4, our y component is negative 1, plus 2. That gives us 9, plus 4 is 13, plus 2 is 15. That means that the equation is 3x minus 4y plus z equals 15. So that will both include this point and be parallel to this plane. Oops, okay. Another equation, this time for a line. So we find an equation of a line parallel to this line and containing the point 5, 2, negative 1. So two parallel lines will have direction vectors that point in the same direction, or at least the direction vectors will be scalar multiples of each other. So our vector, sort of in the direction of the line, well, that's going to be the things multiplied by t here. So it's a 3, that's a negative 1t. There's no t in the z component, so that's a 0. This is sort of our direction vector. And so our line, let's maybe call this r2 of t. I've used r of t up here, so I want to call it something else. It's going to be the point, which I'm going to sort of write as a vector, 5, 2, negative 1, and then plus t times 3, negative 1, 0. In the end, this gives us 5 plus 3t, 2 minus t, and then just negative 1 here. So note, really, it's very similar to this. We have the 3t, we have the minus t, we have no t's here. And instead of having negative 1, 2, and 4, we have 5, 2, and the negative 1. So we're just replacing the point effectively in that equation. Very similar to the parallel plane, problem number 5. Next one. Find the point, Find the point where the line r of t is 3 minus t, 4 plus 2t, comma t, and the plane 2x minus 3y plus 4z equals 6 intersect. So our strategy here is we're just going to plug in 3 minus t is x, 4 plus 2t is y, t is z into the plane equation. We can solve for t then, and then plug that t back into our line, and that should give us our point. So what we're going to get is 2x, but we're going to need 3 minus t, minus 3 times y, which is 4 plus 2t, plus 4z, which is just t. That should equal 6. So we get 6 minus 2t, minus 12 minus 6t, plus 4t equals 6. So we have a minus 8t, we have a minus 4t, minus 6 equals 6. We can move the 4t over there and get negative 12 equals 4t. You see that t is negative 12 over 3, negative 12 over 4, sorry. T is negative 3. So that's not our answer, that's the t. And now we should just be able to find r of negative 3. That should be our answer. So 3 minus negative 3, that's 6. 4 plus 2 times negative 3 is 4 minus 6, that's negative 2. And then we get negative 3. And this really should be a point. I wrote it as a vector, but it doesn't really matter. So our point really is 6, negative 2, negative 3. So clearly that's on this line because we plugged in a value of t that should just give us a point on the line. We can check, is this on the plane? Well, if you do 2 times 6 minus 3 times negative 2 plus 4 times negative 3. Does that give us the 6 that it's supposed to? So that's 12 plus 6 minus 12. 12 and minus 12 cancel. It does indeed give us the 6. So it checks out that this point is indeed both on the line and on the plane. Okay, next one. Let's see, we've got consider the lines. R of t is t, 2 minus t, 3 plus 4t, and m of t is 5t minus 3, negative 2t plus 2, 6t plus 5. We want to find the intersection of the lines. So that intersection here is a point on both. We're going to get r of t equals m. Now it's tempting to put a t in here, but it could be a different value. So for instance, like r of 1 could equal m of 2. So let's just put in an s here. And that's going to give us 3 equations and 2 unknowns. So we'll get a t equals 5s minus 3. And then we'll get a 2 minus t equals negative 2s plus 2. And we'll get a 3 plus 4t for this third component equals 6s. Let's write that a little bit nicer. 6s plus 5. Now we need to solve this. So one thing I'm going to do, how about we add the first and second equations together. The reason I want to do that is t plus negative t will cancel. So I'll get 2. On the right-hand side, 5s plus negative 2s is 3s. Negative 3 plus 2 gives me a minus 1. That gives me a 3s equals 3. 3s equals 3. That tells me if there is a solution, it has to be when s is 1. That is, we have to do m of 1 has to be the solution here. Now to find t, what I can do is plug this s into one of these equations. So how about this first one, because it's already solved for t. So t is 5 times 1 minus 3. It's 5 minus 3. T is 2. So if s is 1, t is 2. So the claim here is that if we have a solution, it has to be when s is 1, that is, it's m of 1, equals r of 2. Now, note, when we solved this, we ignored this third equation altogether here. And so it could be that when we plug in s is 1 and t is 2, that the x and y components match, but the z's are different here. So that's fine. One way to check if this works out is just find r of 2 and m of 1. So r of 2, let's see, that's 2, comma 2 minus 2, that's 0. 3 plus, it'll be 8, is 11. And then we do m of 1, plugged in s equals 1. We get 5 minus 3, that's 2. Negative 2 plus 2, that's 0. 6 plus 5, we do get the 11. So our answer here, intersection point, is 2, 0, 11. Sort of same for both here. Now, I guess in principle, you just try values of t until you find ones that match. That's generally really tough, so we want a more systematic approach. Okay, next question. We want to find the angle between the lines. This is going to end up being the angle between the direction vectors. So this is going to be the angle between their direction vectors. So the first line, the direction vector is 1, negative 1, 4. It's the coefficients of t. And the other vector is going to have a 5, negative 2, 6. So we did a problem earlier on this, finding the angle between two vectors. The formula here was that theta is the inverse or arc cosine of, I'm going to dot the two vectors, 1, negative 1, 4, dotted with 5, negative 2, 6, and then divide by the magnitude of each. This is 1, negative 1, 4, magnitude, times, note that's a scalar multiplication now, times the magnitude of 5, negative 2, 6. And in our case, let's see what this gives us. Let's see, 1 times 5 is 5. Negative 1 times 2 is 2. So 5 plus 2, 4 times 6 is 24. Our magnitudes, let's see, are square root of 1 plus 1 plus 16. 4 squared is 16. Times square root of 25 plus negative 2 squared is 4. 6 squared is 36. here. So what we get is an inverse cosine of 24 plus 5 is 29 plus 2 is 31 over square root of 18 times 36 plus 4 is 40 plus 25, that's square root of 65. So I might just leave this like that. You could multiply 18 by 65, get some larger number in terms of 1 square root. Maybe you could rationalize the denominator. You could also like approximate this with a decimal either in degrees or radians for your inverse cosine. But this gives you an exact answer here. And it's not going to, doesn't appear that it's going to simplify very much. Okay. Next question. So we have a graph of x squared minus z squared equals y cubed plus y squared. So this is almost like one of those quadratic surfaces, but we have this y cubed messing things up. In any case, we can still draw cross sections, which sometimes are called a trace. Here's why this word trace is in here. So we're going to draw a cross section when y equals negative 2. All we need to do is plug in negative 2 for y. So we take x squared minus z squared is negative 2 cubed plus negative 2 squared. So that's x squared minus z squared equals negative 8 plus 4. That's x squared minus z squared equals negative 4. And it's going to be customary to sort of multiply both sides by negative 1. That'll give you z squared minus x squared equals positive 4. So customary to get a positive constant here. Now when we graph that, I'm going to choose to graph this on the xz plane. So I'm going to label x here, z here. We're going to get a graph here. This is a hyperbola, and I have to think about, does my hyperbola, and then does it open this way, sort of as the red direction, or does it open in sort of this blue direction here? So it's one or the other. I'm not going to get too concerned about drawing this precisely, but it's either sort of this blue hyperbola or the red hyperbola. To figure that out, what I'm going to do is, well, if x is 0, here I get z squared equals 4. So if x is 0, z could be positive 2 or negative 2. So when x is 0, we could get a positive 2 or a negative 2. That was going to leave us the blue. Note the red here do not have any points when x is 0. So the red, those are not that's not the correct hyperbola. So it's the blue hyperbola here. Next one. We're going to do a cross section when y equals 0 here. So again, we're just going to plug in y equals 0. So we get x squared minus z squared equals 0 cubed plus 0 squared. Well, 0 cubed plus 0 squared is 0. And so what we get is x squared minus z squared equals 0. That is x squared equals z squared. And that is x equals, well, it'd be tempting to say z, but you could actually have plus or minus z. So when we go to graph this, we're actually going to get two lines, x equals z. It's going to be this line here. We're also going to get x equals negative z is this line here. So this is sort of this x here. So our cross section is an x when y equals 0. Next one, when y equals 1, same thing. We're going to get x squared minus z squared equals, it was y cubed plus y squared. So I get 1 cubed plus 1 squared. So we get x squared minus z squared equals 1 plus 1. That's 2. Graph this again on the xz plane. And again, really this is a hyperbola because it's square minus square. So I either get this blue sort of hyperbola that we had before, or sort of this red hyperbola. Again, I'm not really concerned about scale. I just want the general shape here. Now, if I plug z equals 0 this time, I get x squared equals 2. It means x should be plus or minus 2. It tells us there should be two solutions when z equals 0. Z equals 0 is the x-axis. I get two solutions. Our cross-section is this red cross-section this time. So it's the other hyperbola here. Note here again, the blues didn't have any points where z was 0. Okay, next one, we have a position function. R of t is 1 over square root of 2, t to the 4th plus 5, 7 minus t squared, comma t to the 6th over 3. we want to calculate something. So velocity of t, that's really just r prime of t. Just have to differentiate here. So when we differentiate, we get component-wise differentiation. So it's 1 over square root of 2 times 4t cubed. Derivative of 5 is 0. Derivative of 7 is 0. We get a negative 2t as the derivative of negative t squared. And then we get a 6t to the 5th over 3. It's the derivative of t to the 6th over 3. Probably clean this up a little bit. About 4 over the square root of 2 t cubed, negative 2t. 6 and 3 sort of cancel to give a 2t to the 5th. And then I might rationalize this 4 over square root of 2. So if you do that, you get 4 square roots of 2 over 2. 4 and 2 cancel. You get 2 square roots of 2. So your answer here would be 2 square roots of 2 t cubed, negative 2t, 2t to the 5th. So that is our velocity vector. Acceleration is just the derivative of velocity. So acceleration of t is the derivative of the velocity, or the second derivative of position. So you could start with position again, take 2 derivatives, but you've already got 1, so why not just differentiate that? So what I'm going to get here, not really r double prime, but the derivative of this vector is going to be 3, well, let's do it this way, 2 square roots of 2 times 3t squared. Derivative of t cubed is 3t squared. Whoops. And then the derivative of negative 2t is negative 2. Derivative of 2t to the 5th, let's see, that's 2 times 5t to the 4th. And so we end up with 3 times 2 is 6 square root of 2, t squared, negative 2, 10t to the 4th. So our acceleration vector is 6 square root of 2 t squared, negative 2, 10t to the 4th. Next one, speed. Speed, this is going to be the magnitude of the velocity. So we have a velocity vector up here. What we get is a square root of 2 square root of 2 t cubed squared plus negative 2t squared plus 2t to the 5th squared. And when you calculate that, what you get is square root. So 2 square root of 2, that's going to square actually to 8 here. So we'll get 8t to the 6th plus 4t to the 4th. Whoops. Plus 4t to the 10th. Now I can factor out a 4t to the 4th from this. I'm left with then 2t squared plus 1 plus, let's see, plus t to the 5th here. So that's sort of what I get. I'm sort of hoping for something that'd be a perfect square, and I'm wondering if I didn't make a mistake. Started with t to the 6th. Differentiate, you get t to the 5th. Square that, you get t to the 4th. The other one was t to the 4th. Third, that's 6th. Another one was a t squared. You get a t. Oh, I did make a mistake. So this 4t to the 4th, that shouldn't be to the 4th. That should be a 4t squared. So I can't factor out, let's get rid of this. Here, I can't factor out a 4t to the 4th. I can only factor out a 4t squared. And then I get a square root of 2t to the 4th. If I pull out the 4t squared, plus 1 plus t to the 8th. And then what you get is you get that 4t squared square root is 2t, really an absolute value of t. But I'm going to assume t is positive here, or at least non-negative. This thing inside is a square root of, that's t to the 4th plus 1 squared. So my hope, if this is going to work out nicely, is that I get a perfect square inside. That's one hope anyway. T to the 4th squared would give me t to the 8th. 1 squared would give me the 1. T to the 4th times 1 is t to the 4th, times 2 gives me 2t to the 4th. So if I squared this out, I'd get exactly what I have underneath this square root here. And so that tells me my speed is 2t times t to the 4th plus 1, or you could even write that as 2t to the 5th plus 2t. So maybe this is a nice form factor. Kind of depends on what you want to do with it, if you want to multiply that out or not. Okay, next one, arc length. So from the time when t equals 1 to when t equals 3, well, the formula for arc length, so we're integrate 1 to 3, it's really going to be the magnitude of r prime of t, that is we're integrating the magnitude of v, that is we're integrating the speed. So our arc length, given we have a nice speed formula up here, we're going to use this formula or this formula for the speed. I'm going to choose this second one because that's going to be easier to integrate. So I'm going to do 2t to the 5th plus 2t dt. I just need to integrate that. So arc length is the integral, definite integral of speed here. And so what we get, let's see, 2t to the 5th, when you integrate, you get t to the 6th over 6. So that's t to the 6th over 3, the 2 will cancel the 6, plus integral of t, 2t is t squared, from 1 to 3. So we get 3 to the 6th over 3, plus 3 squared is 9, minus when you plug in 1, you get 1/3 plus 1. Let's see, I could take 3 to the 6th, cancel one of these is 5, and cancel the 3. 3 to the 5th is 243 plus 9 minus 4/3. So let's say what we get, let's see, this is 252 minus 4/3. This is 756 over 3 minus 4/3. So we should end up with 752 over 3 as our arc length. Okay, now we want to find t. This is our unit tangent vector. What this is, t, is in the direction of r prime, but it's a unit vector. So we divide by the magnitude of r prime of t. And so what we get, let's go see, we had r prime up here, that was our velocity. That was this thing, but we're going to divide by the magnitude of r prime of t, which is the speed. So we get 2 square roots of 2. Let me just copy this vector here instead of trying to write it down. I'm actually going to copy. So I'm going to get this whole vector here. I'm going to copy here. Go down here. Click there a bit. And then I'm going to paste. So there's this vector. Put that up here. Let's get rid of that equals there. So this is let's get rid of this equals here. So this is, let's get it back to my pen. So this is r prime of t, but I have to divide by the magnitude of r prime of t, which I could find again, but that was just our speed. That's the 2t times t to the 4th plus 1. So this is 2t times t to the 4th plus 1. And then you can divide component-wise. So what I'll get, see, 2 and 2 will cancel, so I'll get square root of 2. One of the t's cancel, I get t squared over t to the 4th plus 1. Negative 2t over 2t will give me a negative 1 over t to the 4th plus 1. 2 to the 5th over 2t will give me a t to the 4th over t to the 4th plus 1. So this is our unit tangent vector at any time t. Curvature. So the curvature we can calculate in various ways. One way to do this, I mean, really what we want is it's dt ds, but it's the magnitude of that. So it's the derivative of the unit tangent vector with respect to arc length. A nice computational formula for this is dt times dt ds, magnitude of all this, which really gives us dt magnitude times 1 over ds dt, that's absolute value. So this ds dt, what that's going to be here is that ds dt, that's our speed, really, magnitude of the change in position with respect to time. So that's our speed And this dt is going to be a little bit of a mess. We have to differentiate this thing up here. So what we're going to get when we do this, I'm going to write the 1 over ds dt first, 1 over the speed. Our speed was this 2t times t to the 4th plus 1. So it's 2t times t to the 4th plus 1. And then the derivative of our unit tangent with respect to t, I'm going to do this component-wise. So the first, I have to do a quotient rule. Bottom, t to the 4th plus 1, times derivative of the top is 2 square root of 2t, minus the top, which is square root of 2t squared, times the derivative of the bottom is 4t cubed, all over the bottom squared. Second component here, let's see, I'm going to get, I could do a quotient rule here. Let's just do that. So it's bottom times the derivative of the top, but the derivative of the top is 0, so I don't need that. So it's top minus top times the derivative of the bottom. So what I'm going to get is minus -1, that's plus 1. So I get 4t cubed over t to the 4th plus 1 squared. And then my third component here, or third, I'm going to get bottom, t to the 4th plus 1, times the derivative of the top, 4t cubed, minus the top, t to the 4th, times 4t cubed is the derivative of the bottom, all over t to the 4th plus 1 squared. So I'm just differentiating my unit tangent vector with respect to t. Gives me this mess here. So what I get here, let's go through this. I'm going to have to sort of use the space here for the next question just to simplify this out a bit. So I'm going to just keep going. So let's forget about this for now. I get 1 over 2t times t to the 4th plus 1 times the vector. So you could distribute this through. You get t to the 5th times 2 square roots of 2. You get 2 square roots of 2 t to the 5th plus 2 square root of 2 t minus 4 square root of 2 t to the 5th over t to the 4th plus 1 squared, comma 4t cubed over t to the 4th plus 1 squared, comma, I'm going to get 4t to the 7th plus 4t cubed minus 4t to the 7th. So we'll cancel, which is nice. T to the 4th plus 1 squared. I can pull out that t to the 4th plus 1 squared. I get 1 over 2 times 2t, I'm sorry. Let's rewrite that. So I get 1 over 2t times t to the 4th plus 1 cubed. Pulling out this denominator from each of these. For here, I'm going to get a 2 square root of 2t minus 2 square root of 2 t to the 5th. 2 square root of 2 minus 4 square root of 2 is negative 2 square root of 2. You get a 4t cubed, and then the 4t 7th minus 4t to the 7th is 0. I'll get a 4t cubed here as well. And then when I do my component-wise division, forget about this one for now too, what I get when I divide by these things, let's see, I'm going to get the first component, I'm going to get a 2 I can cancel out. I can cancel out the t's, so I'm going to get a square root of 2 minus square root of 2 t to the 4th over t to the 4th plus 1 cubed, comma, let's see, I'll get a 2 t squared over t to the 4th plus 1 cubed, and then I'll get a 2, same thing actually, 2t squared over t to the 4th plus 1 cubed. So that big thing here, that is our, oh sorry, and I made sort of a mistake here. That's not our curvature. I found this without taking the magnitude. So now I need to take the magnitude of that vector. So this is not our answer. Here we need to find the magnitude of that vector. And so our magnitude, I'm going to pull out the t to the 4th plus 1 cubed. I'm going to get 1 over t to the 4th plus 1 cubed times the magnitude of the rest of this, just square root 2 minus square root 2t to the 4th squared plus 2t squared squared plus 2t squared squared. So this is going to be, whoops, no vector here at all, 1 over t to the 4th plus 1 cubed times the square root of, let's see, we'll get 2 minus 2t to the 8th, not 2, plus 2t to the 8th, and then we get square root of 2 times square root of 2 is 2, times another 2 is 4, minus 4t to the 4th, and this is going to be plus 4t to the 4th plus 4t to the 4th. Cancel out, whoops, I wrote t squared, said t to the 4th, I believe, here. So I can cancel out one of these 4t to the 4th there. I can pull out a 2, and what I get is 2 over t to the 4th plus 1 cubed times square root of t to the 8th plus 2 t to the 4th plus 1. That works out to be 2 over t to the 4th plus 1 cubed times, so this here is going to be, let's see, t to the 4th, well, square root of t to the 4th plus 1 squared. So I'm going to get 2 t to the 4th plus 1 over t to the 4th plus 1 cubed. So the whole thing, when I'm all said and done, my curvature is 2 over, I can cancel this factor with one of those, and I get 2t to the 4th plus 1 squared. So that's my curvature. Okay, I'm going to stop this for now. We'll pick up the rest of these later. I've got to clean up some of what I've got going on here.